I said I was done with the Kalman filter. I lied. I'd like to go over this paper. The purpose of the paper was to see how well we could track maneuvering targets, other airplanes. Um, this was a paper that came out in 1970, but in IEEE transactions on aerospace and electronic systems, which is a fairly impressive journal. Um, but I think if you've gone through this whole course with me, my random processes and common filtering, I think you could do everything in this paper. So let's look at some of the highlights of this paper. This little equation, that is a continuous time process equation. Uh, right here, it's just a state vector x position, and you should say velocity here, position and velocity of your vehicle that you're tracking. And he's interested in other airplanes. The input is acceleration. Here's the F and G. You should be fairly familiar with that. Here is the autocorrelation function that he's assuming for acceleration. You look at this is what we call the Gauss-Markov process. We've seen this very autocorrelation function, I think, multiple times when we talked random processes and, and going through linear systems. Here's a funny one. How do you model? See this sigma sub m? That's the maneuver variance of the targets. How do we know what that ought to be? Here's what he did. He said, "Oh, I'll say the acceleration is between some plus and minus maximums, and they each have some discrete probability there. There's another probability that it doesn't accelerate at all, and everything between the min and max we'll just assume is uniform." Here you have a mixed distribution, mixed continuous and mixed discrete. We talked about that when we talked about probabilities in module one. In fact, I think I made this a homework problem for my students. Um, this is a graph of that autocorrelation function for the acceleration. And what else does he do? Oh, we get the acceleration by sending white noise through this first order linear system. Remember when we did, I think that was random processes through linear systems, probably module 4 in my course, shaping filters, whitening, uh, and that allows you to add a state for acceleration. So now we have a 3-state little process with position, velocity, and acceleration. I'm just trying to show that you've seen a lot of stuff in this paper. So there we have what it is in continuous time. Then the next thing you got to do is discretize it. And I think that was module 5, state space and discretization. We want to go from continuous time to discrete time. And he goes through that mess. Comes up with this for the phi matrix. One of the limiting cases of this is the so-called Newtonian matrix. You don't need to go there right now. But if you look at all this is that business we did when we quantized it, discretized it. What else does it do? the only measured position. When you discretize, you got to come up with the Q matrix, and he leaves that for appendix. It is pretty tedious. We did a little bit of this, I believe, in one of my modules. I think in the discretization module, state base. Yeah, that took quite a bit of calculation. You could have done it, but it would have been pretty tedious. Oh, here's something I wanted to remark on. When I talked about initialization, I said there's two ways to do it. He chose the way where you use measurements to initialize. And he has to have this whole procedure, this sort of algorithm, because you've got a three-state vector, position, velocity, and acceleration. But he's only measuring position. So it's going to take him like 3 measurements to actually fill a complete estimate of the state. So you got to have this whole little algorithm to start. I kind of think that's overkill. What else? Let's go back and remember when I said you can figure out your covariance matrix stuff without actually taking measurements. That's what he's doing. That's what this paper is based on. We're just saying how accurate could we track something just based on our model of the system and using the Kalman filter equations. And that's what these graphs are. I'm not going to go through the graphs, but they're what you crank through with the Kalman filter gain and covariance equation. Where you don't really need the measurements. We're using the Kalman filter equations to do analysis, not to actually do the estimating. We're going to find out how accurate we could possibly do things. Is there anything else worth saying about it? I just wanted you to see in this paper a lot of things we talked about in this course. Probability through random process through a linear system, state space and discretization, and finally the Kalman filter, all in here. I think I'll stop there, but I just wanted you to appreciate a little bit of that.